Okay, so we went through most of the background we need to get to this point where we are going to jump into the equations of motion. So we have to derive a few things, which is really fun, but it's also good to make sure that you don't lose the most exciting physics by getting stressed about the equation. So let's try to have some fun with this. So this is the example of a satellite image compared with the lab experiment. So John Marshall and Alan Plumb kind of tried to give you a sense of the physics from the lab experiments and then try to show why they are analogs of what actually happens on Earth, right? We will see in this equation when we derive, in this chapter when we derive the equations, that going from a flat tank in a lab to a sphere is a bit tricky, but there are a lot of fun things to learn. So these angles at which things are appearing on this satellite image, these swirls, we kind of mentioned. We will see a little bit later on that the northward transport, considering the wind directions and so on that we have looked at, require some special dynamics, circulation, includes instabilities and so on. But you can still see kind of the similarities. Here is the lab experiment again, with cold, ice cold temperatures in the middle and warmer temperatures at the outer edge. And at some rotation rate, you will begin to have these swirly motions where the cold temperatures from the inside are going out to the warm edge outside, and the warmer waters outside are swirling into the colder side. So that's kind of a analog of this kind of features you see here. So it's the rotation that creates some pretty cute scales and features and dynamics that we will learn about. So let's establish a few simple things first. This we looked at in the case of gravity waves, where we said if the flow is going over a hill or a bump, then the air rises, cools, and you can get condensation of the water vapor and a cloud at the crest of the wave. And based on the flow and the wavelength of the wave that's generated and so on, you can have the cloud anchor to the mountain, like the lenticular clouds that we talked about. So we'll imagine a simple situation where there is a wave in the leeward side of the mountain that continues, where when the wave is at its crest again, there is condensation and clouds. So we have somehow formed a stationary pattern. So we want to understand the simple derivation of equations, in this case for various properties of the fluid. Okay, so let's look at this first as a point. So let's just say we are sitting at the top of the mountain and we're just watching what's going by. Okay, so then you can look at, let's say, change in the cloudiness. Okay, and since you're at a fixed point, you're just looking at the local rate of change in time, dc dt, and since this is a stationary wave, as we said, the cloud properties are not changing. So if you're sitting here, you're always seeing a cloud. So then dc cloudiness dt, partial dc dt, is equal to 0. But that's usually not what we do. We typically try to follow a parcel. We are back to our parcel, or a particle, along the flow. So we have to write our equations for that. So if we sit on a particle and follow the flow, then we are going through clear air, cloudiness, warmer compressed clear air, and again cloudiness, and so on. So the cloudiness along a fixed particle is not constant. Make sure you understand this. Okay, the fixed in space is called Eulerian derivative, Eulerian change, obviously after the historical figure Euler. And when we follow the particle, then the property of cloudiness is not constant. So the delta C, the change in cloudiness as we follow the particle can be written as its change in time times delta t. Again, arbitrarily small steps have to be taken for continuity of derivatives to be valid. So plus dc dx delta x, how cloudiness changes in the x direction, how cloudiness changes in the y direction, and how cloudiness changes in the z direction. So let's say x is along this flow here, y is going, let's say, into the plane of the screen, and z is this vertical scale that we are looking at away from the surface. Okay, so that's fairly simple expression. You should get comfortable with it. Delta c equals partial c partial t delta t, partial c partial x delta x, partial c partial y delta y, plus partial c partial z delta z. So what is delta x, delta y, and delta z? If the particle is moving in the x direction with velocity v, y direction with v, and w direction with z direction with w, then we have delta x is u times delta t. It's a small step change. Delta y is v times delta t. Delta z, change in height, is w times delta t. Fairly straightforward. So we plug it into our delta c and take delta t out. Each one has a delta t. So then we can write it as dc dt, u dc dx, v dc dy, and w dc dz. You know where this is going. So you can take delta t on this side. So dc dt of a fixed particle in this case is then dc dt plus u dc dx, v dc dy, w dc dz. Some of you probably seen this. This is what is called the total derivative, the material derivative, the substantial derivative, the Lagrangian derivative, and so on. Right? That's the total change of a property because of temporal and spatial changes in every direction. Very good. So if we follow a particle instead of sitting in space, this is what we get. That's how the property of cloudiness would change. Using vector notation, we can write d dt as d dt plus u dot grad. Grad is a gradient, so that's the operator d dx, d dy, d dz. You can think of it as I d dx plus j d dy plus k d dz, where I, j, k are the unit vectors, right? I think you've seen this somewhere as well. And u dot is the dot product. Hopefully you have also seen it. If not, you must brush up your vector calculus. Fairly straightforward, but very important for this particular chapter, because I'm not going to spend too much time with the basics. You'll have to catch up yourself. Okay, so we'll take this forward and derive the equations of motion.